Yes. Okay, now it's time to start our webinar. Today we welcome Professor Motoyuki Sato, who was working at Tohoku University in Japan, and now he established and running a company, his own company. And okay. Professor Sato is very actively working, and he's going to the Cambodia or Ukraine and to detect us on the mine. Also, he developed some equipments. So today he introduced a basic background and theory and application, such kind of things. So Professor Sato, please start your presentations.
Okay, thank you very much for introduction. I'm Motoyuki Sato from Tohoku University, Japan. So I will start to share my slide. Okay. I'm talking about the ground penetrating radar. In short, we call it GPR. And I'm very happy to have this opportunity to give a presentation on this topic. Just a moment. Okay, so I think most of you are very familiar with remote sensing. It's a quite general terminology about remote sensing. So remote sensing is a technique used to gather information about the environment and the surface of the Earth from a distance. And I think most of you think about the remote sensing technique used for spaceborne satellite and microwave remote sensing or these kind of techniques. But just to think, if you see on the ground surface, can you see anything under your foot? So subsurface is a environment or a space that we cannot see directly by our eye. So if you use electromagnetic wave or the radar technology, we can see the subsurface structures. So we think that subsurface imaging is also a kind of the remote sensing and gather information about the environment. So it really fits to the definition of the general definition of the remote sensing. So ground penetrating radar, GPR, is active microwave remote sensing for subsurface. Okay. Okay. I think not so many people have ever seen what this GPR equipment looks like. So this is a very typical GPR equipment, and he is just moving this cart, but at the same time, he can see the subsurface structures. This type of the GPR is commonly used for detection of the buried pipe. So here I'm listing the application of the GPR, detection of the buried pipe or cable under pavement, or the detection of the rebars in concrete wall, or the road pavement inspection. And some special application such as archaeological survey or the landmine detection. The landmine detection is one of the topics that I wanted to focus today. Okay, so you can see our students are moving the GPR equipment on the ground surface. So if you transmit electromagnetic wave from the radar antenna and reflected from the target subsurface, we can measure the travel time from antenna to target. So that is basically what the GPR survey does. Okay, this is another animation how the data, GPR data will be acquired. So transmitting antenna transmit EM wave, and the wave penetrate into ground into the soil, and some of the electromagnetic wave reflected from subsurface target and received by the receiving antenna. So now the transmitting antenna and receiving antenna is moved simultaneously. So we can receive many signal diagrams, as you can see here. But normally there are too many data sets. We will just show in such a diagram. And the hyperbolic curve that you can see is a reflection from the point target. So this is a very typical procedure that we acquire the GPL data and image. So this image is almost like a vertical section of the structure. In a GPL terminology, we say normally the three types of the images. The left one, A scan. This is one of the signal where when the transmitting antenna, receiving antenna is fixed on one position and we receive the signal. So we can obtain one signal. But as I have shown, we acquire many data sets. And we set these many data sets in parallel, and we can see the second one. Normally, this is called B scan. So B scan is almost like a vertical profile of the subsurface structure. And if we acquire data not only along one line, but in the parallel lines, then if you cut the data horizontally, we can see the horizontal slices. So that is the third one. And normally we call it a C scan. So A scan is very simple, B scan is two-dimensional, and C scan is normally three-dimensional. Okay, I show one video that we did an archaeological survey in Egypt. So the red box is a GPL equipment, and our colleagues are the pulling radar equipment. We have a RTK GNSS, and we can also acquire the position of the antenna. And then we plotted the GPL response on the Google map. And you can see the two pyramids. And the blue lines with a red dot shows the GPL profile. This is a C scan. This is a horizontal slices. And we can see some red points. We could find that some subsurface object is lying on that position. It's very large scale measurement. And the GPL survey area is almost like 100 meter by 100 meter. And our colleagues started excavate in these positions. So this figure shows the one part of the excavated area. So that cliff that you can see is an excavated site. And below you can see one of the B scan image. So you can see the inclined, you can see the inclined slope on the B scan GPL image. And it very clearly corresponds to the actual geological structure. One person with a white jacket is standing, and just from his foot, there is a slope you can see. And that shape of the slope is exactly fit to the GPL profile, B scan. So this is one of the examples how GPL can image the subsurface structure. Okay, again, very similar figures, but when the radar is moving, dependent on the distance from antenna to the target, we can see the received signal. And the arrival time of the receiving signal is changing dependent on the antenna position. And then we can find the object. But what we can see from here in this figure is that the shape of the reflected signal is not necessarily same as the shape of the subsurface object. That is quite a common situation for any radar measurement. So even if we have a one point target in the left figure, it is written object space. If you use a radar, and if the radar is scanned along the one line, we can see the hyperbolic curve is a middle figures. And the radar acquire such an reflected signal. But as I mentioned, this signal shape is not exactly same as the original shape of the object. So we need a focusing. This focusing is normally referred as a synthetic aperture processing. And after the synthetic aperture processing, we can reconstruct the original shape of the image. And on the right figure, the image space, we can reconstruct the shape of the object. That is a point. Okay, that is what we are doing. So this procedure is exactly same as signal processing used for spaceborne microwave remote sensing, that is a synthetic aperture radar processing. But exactly the same procedure can be applied to GPR. Just I want to note that the sub-processing is equivalent to so-called migration processing, and migration is normally used as a terminology in the seismic signal processing or the GPR signal processing. But the migration and the sub-processing is exactly the same. This figure indicates how sub-processing is working. Okay, we can measure the distance from the transmitting receiving antenna position to the target. And what radar can measure is the travel time from antenna to the target. And what sub-processing is doing is that if we measure the travel time, we can estimate where the reflection signal appears. And we gather all the estimated reflection time, reflection signal to one position. So that is what sub-processing is normally doing in a very simple way, simple explanation way. But in this case, we can measure the travel time. But in a sub-processing, we can reconstruct the image by using the position information. So that is not the time domain, but it is a space domain. So time domain signal have to be converted to the space domain signal via electromagnetic wave velocity. So the equation showing this figure indicate that the travel time tau is a distance divided by velocity v. Okay. When we do the sub-processing for the spaceborne remote sensing, the v is an electromagnetic wave propagating in the space. So this is a constant. But if we do the processing for the GPL, v is the velocity of the electromagnetic wave propagating in the, inside the soil. And the velocity of the electromagnetic wave soil is not a constant. That is a very important point. Okay, I show one example how the GPL processing, sub-processing applied to GPL works. Okay, upper figure shows one of the B scan. It's a low signal. Okay, the horizontal axis is about 15 meters, and the vertical axis is the travel time. And we can see several hyperbolic curves in this B-scan profiles. In the figures in the bottom is a sub-processed image. Now we can see the one black point located at the horizontal position around 12 meters. Okay, this is a round shape. Okay, that corresponds to the reconstructed image from one of the hyperbolic curve we can see in the upper figures. But if you see other hyperbolic curves, it is not reconstructed as a point. In this case, the target is a buried pipe in soil. So if the image reconstruction or the sub-processing works correctly, all these hyperbolic curves should be reconstructed as a point image. But in this case, only one hyperbolic curve is reconstructed as a point. That is because the inhomogeneity of the soil. Normally, the soil electromagnetic wave velocity in soil varies very much. If you just measure the section of the 10 meter, maybe the velocity can be changed more than 30%. And SAR processing requires the exact velocity value to reconstruct the correct image. But for the soil, we cannot know the exact soil. Therefore, the sense aperture processing cannot reconstruct a very accurate image of the original target. So that is one of the most important and most serious problem of applying the sub-processing to GPL. But to some extent, it works. So we have to know the relationship of electromagnetic wave in soil and the physical parameters. The most important physical parameters that control the electromagnetic wave velocity is the soil moisture. So this figure shows the horizontal axis is soil moisture from 0% to 100%. 0% is a completely dry soil, and 100% is 100% filled with water. The vertical axis shows a direct constant, epsilon r. And the equation written on the above in the blue box is V is the velocity of electromagnetic wave, and C is the electromagnetic wave in the vacuum, and the square root of epsilon E is the direct constant inside the square root. So velocity of the wave is related to the direct constant. And the direct constant is almost proportionally related to the soil moistures. So we can understand electromagnetic wave in soil is related to the soil moisture. So always we have to think about the soil moisture for better processing applied to the GPL. Okay. So since aperture processing can be applied to GPL, but still there are other things that we have to consider. Okay, the above figure shows the situation of the space-borne sense aperture radar. So when spacecraft flies along the flight path, it has a relatively large or the wide antenna radiation pattern. And the black dot shows the position of the target. So while the antenna radiation pattern covers the one target, these data can be used for the sense aperture processing. So normally we can call it a sense aperture length. And this sense aperture length is normally very, very long, maybe a few hundred kilometers for the spaceborne SAR data acquisition and processing. But the lower figure shows the situation for the GPL. Okay, the situation is the same. GPL can move on the ground surface. This is the survey line. But the antenna is so small. Therefore, the antenna radiation pattern is also relatively wide. But if the electromagnetic wave propagate inside the soil, it's suffered from very strong attenuation. Therefore, even if the radiation pattern, theoretical radiation pattern covers that target, in many cases, the propagation length is too long, then signal will be attenuated. Then we cannot receive the signal. But in the spaceborne case, even if it is very large distance, there is no attenuation. So it is easy to acquire to receive the signal. But for the GPL, the longer distance target cannot be measured because of the electromagnetic attenuation in soil. So practically, the sense aperture length of the GPL is very short unfortunately, that I showed in this figure as a brown color. So blue color is a theoretical antenna radiation pattern, which is very large. But the actual area that the GPL can acquire the data is very short. So since aperture length is very short for GPL. And we summarize this situation and compare spaceborne SAR and GPL. So since aperture length for the spaceborne SAR is very large, but the GPL is limited. And attenuation of electromagnetic wave in medium for the spaceborne SAR is almost negligible, but the GPL is very large. And the medium property, that means the spaceborne SAR, the medium is a space, so it is quite homogeneous. But for the GPL, it is soil. Soil moisture varies, so it is strongly inhomogeneous. So azimuth resolution of the SAR processing is related to the since aperture length, but for the spaceborne SAR, from the theory, we can see that the azimuth resolution can be defined by the antenna aperture size, and it is known that the azimuth resolution is independent of the distance from antenna to the target. That is a quite important property for the since aperture processing. But for the GPL, since the aperture size is limited and relatively short, that kind of mathematical ideal situation cannot be satisfied. Therefore, azimuth resolution is defined by the actual antenna size and also dependent on the distance. For the GPL case, distance is depth from the ground surface to the target. And so resolution is normally not so good compared to the spaceborne SAR. So there are many disadvantages for the GPL, unfortunately. So in summary, SAR processing for GPL is suffered from inhomogeneity of the medium. Medium is the soil, and strong attenuation, and short since aperture length. So we think that subsurface imaging is not so difficult because the target is very close. Normally, the buried pipe is only 50 centimeters or 1 meter below the ground surface. But the spaceborne satellite is flying over several hundred kilometers over the ground surface, and the target is very, very far. But in practice, the GPL imaging is, I think, normally more difficult than the processing for the spaceborne since aperture radar. Okay, now I show one example. This is a radar image that was acquired for the landmine detection. And now I move the image. Now you can see the image is moving. So this is a C scan. These are horizontal slices. And I have moved the depth of the slice. In the middle, I repeat this image. In the middle, you can see the red and blue round shape. This is a landmine. So the same shape of the landmine is a pure circle, but you can see this is deformed because of the inhomogeneity of the soil. So since image reconstruction by SAR is not perfectly working, but quite roughly we can see the shape of the image. Now we talk about the humanitarian demining and how the GPL works for that one. I think most of you have ever seen these figures. This so-called metal detector detecting the landmines. I took this picture in Afghanistan. So-called metal detector is a electromagnetic induction sensors, which uses Faraday's law to detect a metal object. Okay, it is a very good sensor, but there are many fragments buried in the soil, in the battlefield, former battlefield. Very typically, in order to find one landmines, we have to find we have to dig up more than 1,000 metal fragments. Metal fragment is a piece of the fragment of the bombs or the other small metals. And the metal detector can detect a very small metal part included in anti-personnel landmine. So it still works perfectly. But the problem is that we cannot discriminate these small metal in a mine from other simple metal fragments. So that's why we wanted to introduce GPL. So metal detector detects metals. And if you can use the GPL at the same time, we can see the shape of the object. So if the GPL can see the target shape, then it is a mine. Okay, at first we hear the sound of metal detector and try to find the position of the object. And we start to acquire the data by pushing the button and stop the data acquisition. And processing start, and from metal detector we can find the object, and from GPL we can see the object here. Yes, I developed this white and blue sensor. This is a so-called ARIS. This is an advanced landmine imaging system. This system is equipped with a GPL and EMI sensor, that is a metal detectors. And this sensor can image the object. So this A scan, B scan, C scan that was acquired by our sensor. Okay, as you could see on the animation, I scanned the sensor by my hand. So we use an accelerometer to track the position of the antenna. And the scanning is not a straight, but it's a two-dimensional scanning that you can see here this way. And then using this data, we will apply three-dimensional sync aperture processing to the data. These two figures show the horizontal slices, C-scan images dependent on the depth. The left figure shows the raw data. The data was plotted just below the position where it was acquired. We cannot see anything. But this data set was processed by using a sync aperture radar algorithm, and we can obtain the right figures. In the right figure, you can see the red and blue shape continuously appearing. That is a landmines. So we can find that the SAR processing can reconstruct the actual shape of the landmines. It is quite useful. And as I mentioned, the velocity of the soil. If the soil velocity is not correctly estimated, the shape of the target can also varies. Okay, so this is the same figure. So after assuming the correct velocity of the EM wave and acquiring the data, we can have a very good image of the image of the landmines. So after we have developed this sensor, we have deployed our GPL sensor in several mine affected countries. So this video shows how our sensor is working in Cambodia. So the left figure shows how the data was acquired, and the right figure shows the female operator shows us that she detected one landmines in the morning that when I visited there, and she's showing the sensor's image. Okay, so our sensor has been tested in Cambodia, and humanitarian demining is very important after the conflict finished. And in Cambodia, the inner conflict is almost over in 1990s. And then after the humanitarian demining activities have been conducted for many years. This figure shows the one of the sites where our sensor was applied for the landmine detection. The left figure shows in March, and the right figure shows the same location in October. The building that you can see is a Buddhism temple. And the same location we could find after the removal of the landmine, the farmers, local farmers can use this rice paddy. And then I just want to introduce our activities in Ukraine. So the landmine issue in Ukraine started not from 2022, but 2014 in Crimea issues. Landmine problem has occurred in Ukraine. And after the intrusion of the Russian troops to the Ukraine, that problem is unfortunately increasing in this moment. So there are many areas, vast areas, where the landmine have to be removed in Ukraine.
Japan stands with Ukraine. To accelerate landmine removal in Ukraine, Japan is conducting training in how to use landmine detectors based on its experience in Cambodia. The training focuses on cutting-edge Japanese landmine detection technology. I hope this technology will contribute to the safety of Ukrainians in their everyday lives. Japan stands with Ukraine.
Okay, so we delivered our sensors to Ukraine, and these sensors is now being used in Ukraine for the landmine detections. I visited Ukraine 2 times, and last March I took this picture in the Kyiv. Okay, and this is the picture when I trained the Ukraine operators about the operation of the GPL sensors.
It's being used in war-torn Ukraine. Sato hopes it can provide a foothold for
Okay, so the process is not very fast, but our sensor has been deployed in a Ukraine demining team, and now they started to use our sensors. So GPL is not a simple sensor. As I mentioned in my presentation today, we have to think of the soil condition for better image reconstruction. Even if the sense aperture processing is used, if the velocity is not correct, it cannot reconstruct a good image. And also physical parameter of the soil and also target is related to the quality of the image. So landmine detection, we do not just deliver our equipment, but we have to go there on the site and observe the operation, and we have to scientifically consider how these sensors can be usefully applied for imaging. And that's why I often go to these landmine affected countries to support their operations. So summarizing my talk. So the sensor that we have introduced today, the AIRIS, is the world's only mine detection sensor capable of the imaging GPL. So normal metal detector hears only the sound. And there is also some GPL equipment that can be used for the landmine detections. But only our sensor is using the SAR processing because our sensor can acquire the position information. Other GPL sensor normally shows only B-scan, that is a vertical section image. And so we cannot identify the target. Maybe stones or the tree root looks almost the same as the landmines, but our system can identify the mines. And I repeatedly mentioned that the SAR processing for GPL is harder than that for the spaceborne SAR. Maybe you can understand what I'm talking. So I think that this GPL application in landmine is one of the very good examples of the practical use of the electromagnetic wave imaging. So quite generally, sense aperture radar is a EM wave imaging methodologies, but the GPL is a special application. But it is quite usefully used in these days. I think at least for the Ukraine issue, I hope some discussion with Putin and Zelensky will go well on next Thursday. But even if the war has finished, we expect that the landmine clearance in Ukraine takes more than 20 or 30 years from now. So we hope our technology can be contributed to these mine affected countries. So I think I finished my presentation. Thank you very much for your attention.
Professor Sato, thank you very much for your very impressive talk. And we learn a lot about your technique and the principle of the technique and the application of the society. So actually, we have many questions for the Q&A sections. Lakshmi, can you introduce the question each by each to Professor Sato?
Yes, sure. So thank you very much once again to the professor. It was very interesting and very informative. So I'd like to start with the first question. So the first question says, how reliable is GPR in discriminating between actual landmines and other metallic clutter in the subsurfaces?
Okay. It's strongly dependent on the experience of the operators, unfortunately. So as I mentioned, so the image that we can obtain our GPL sensor is not exactly the same shape of the target, and it is deformed. And so the operator, we normally call this operator as a deminer, operator who will do the demining, called the deminer. The miner have to have the experience how the object looks like. And in mine field, normally we have a priori information which type of the landmine is used in the specific area. So in most cases, the deminers know the shape of the size of the target that they have to detect. Then they can discriminate the other targets like stones or the tree root from the real target. Normally, metal fragment is very small or the large. Some cases very almost the same size as the landmines. But from the shape, they can classify. But of course, we cannot make any mistake. So mistake have to be always the safe side. So we don't discriminate the landmine 100%. Maybe in order to find one landmine, I mentioned conventionally we have to dig up 1,000 metal fragment. But we think if you use this GPL technology, from 1,000, we can reduce the number of the excavation maybe up to 50. Then 50 to 1 is the ratio of the metal fragment to landmine. So I think this kind of ratio can increase the efficiency of the landmine clearance operation.
Thank you so much. So the next question goes like this. I have a question. Can you explain the differences between GPR and borehole radar in terms of data acquisition and application scope?
Okay, it's very interesting. I didn't mention anything today, but also my specialty is a borehole radar. Okay, borehole radar is one of the GPL equipment, but used in a drilled borehole. Very typically, GPL use a frequency. I didn't mention of the frequency today. I'm sorry. My GPL, our GPL equipment used for the landmine detection uses a frequency from 800 megahertz up to 2.6 gigahertz. Okay, around a few gigahertz, 1 or 2 gigahertz electromagnetic wave can penetrate in the typical soil, maybe only up to 30 centimeter to 50 centimeter. The range is very, very short. But for the borehole radar, normally we wanted to see the very large distance. So in order to generate the lower frequency, typically 100 megahertz is used for the borehole radar. Antenna size is more than 1 meter. So it's a very large antenna. So it is very difficult to handle these large antenna on the ground surface. But we can insert these long antenna in a borehole. So in a borehole, we can use a low frequency. And then it can penetrate maybe 20 meter or something like that. So normally, borehole radar is used to detect an object that is lying very deep subsurface, maybe 10 meter, 20 meter, and some distance from the borehole, maybe 10 meter or 20 meter penetration can be achieved. So the application is different, but the principle is, of course, the same.
Thank you so much. So I think the third question is the repetition of first question. So let's go towards the other one. So the other one says, in the context of landmine detection, how do GPR system perform in different soil types or weather conditions?
Yeah. If you have the heavy rain, the soil gets wet, and then the GPL does not work very well. But normally, if it is an agricultural soil, the soil is very soft, so the rainwater can penetrate in the soil, and the soil can get wet. But in most cases, in a minefield, it is not used for the agriculture activities. So the soil is very hard. And so even it rains heavily, the rain does not penetrate to the soil so much. So the soil moisture does not change so much. But if it is very muddy, of course, the electromagnetic wave cannot penetrate. So normally, landmine detection in a dry soil condition is better. But even if it rains, it still works. But there's other issues. If it rains or it has very heavy rain, normally the miner cannot walk outside. So we do not do the landmine detection activities when it is raining. But after the rain it just stops the raining, we can continue the work. Of course, the soil moisture also affects somewhat.
Thank you so much. So here are, I see two of the questions are very interesting kind of ones. This question says, are there any specific adaptations you had to make for GPR systems deployed in mine-affected regions like Cambodia and Ukraine?
Yeah, that is also very important. So I mentioned that normally I want to visit the site to optimize data acquisition and processing. I didn't explain about the system very detailed, but that white and blue sensors that I showed in the video is a radar equipment, and all the data is transferred to the smartphone. We are using the Android smartphone by Wi-Fi connections, and all the sync aperture radar processing is carried out on the smartphone. And then we can change the velocity value in the processing. So as I mentioned, the estimation of the velocity is very important. So normally, Cambodia and Ukraine has a different soil properties, different soil moisture, and the conditions are different. But our software is adaptive. So we control normally the electromagnetic wave velocity to have the better image. And that's what we have to do. And that is somewhat a bit difficult for the local operator, the miners, to do that. So we will give some suggestion to the local operators to optimize these conditions. That is what we are doing. So basically, hardware is the same. And the software parameter should be changed, optimized for each site. That is the answer.
So the next question says, have you encountered any ethical dilemmas or societal challenges when you were deploying GPR technologies in conflict-affected areas like Ukraine? A bit non-technical.
It's a really bit difficult question, Sam. Unfortunately, in this moment, access to the Ukraine is very, very limited. Normally, the humanitarian demining can be carried out only on after conflict areas. So we do not do these activities while the war is running. Okay, so Ukraine is a very exceptional case. So, but we are partially doing the demining activities in Ukraine, but of course we do not do that by myself. What I'm doing is that we are training the deminers and explaining the technology to them. And actual demining is carried out by the local deminers. So in Ukraine, only Ukraine deminers working for that. Maybe this question is quite general, and this is unfortunately this is not the technical the question, but how we can introduce this technology is related to how should I say the feeling of the local inhabitants and social condition and everything. So it is very important, but I don't have a very clear answer to this question, so I'm very sorry.
Thank you. I think you answered it very well. I mean, even as a technical person, thank you so much. So another question goes like this. Thank you very much for such a great presentation. How do you see AI or machine learning being integrated into GPR data interpretation workflows in the future? Or
Yeah.
maybe, I mean, it might have been implemented to some extent, right?
Yeah, actually, we are doing now. The data acquired on the smartphone can be stored. So all the data is stored on the smartphone, and we can download all the data, and we can accumulate all these data set in the real minefield. So these data can be used for machine learning. So we can have quite a lot of the data set. This is not a simulated data set, but it's an actual data set. So now we are planning to apply the AI technology, and maybe it to be give a suggestion or the support to the deminers. So deminers have to observe the image of the smartphone and have to recognize mines. So I explained that they need experiences, but maybe AI can support that kind of the judgment. So I think it is quite useful. So and we already have started to work for that.
So another question is from Tamer. It goes like this: Professor Sato, do you think that GPR technology can be implemented in small drones for faster scanning?
Yeah, that is also important question, but the answer is unfortunately no. So GPR antenna is set very close to the ground surface. It is because if the antenna is very close to the ground surface, electromagnetic wave is absorbed in the soil. It is very interesting. Most of the electromagnetic wave will be reflected on the ground surface. For example, from the spaceborne SAR, the radar signal will be reflected from the ground surface object. So we can see the surface object images. But if the antenna is very close to the material and the distance is less than 1/10 of the wavelength, so in our case, maybe if the antenna is closer than 5 centimeters from the ground surface, electromagnetic wave is not totally reflected from the ground surface, but most of the energy is absorbed in the soil. So it is related to the boundary condition of the antenna element and the soil. So it is a very, very interesting phenomenon. So if the antenna is very close, we can see the ground subsurface conditions. But the drone cannot fly such a low altitude, at least 10 centimeter to 20 centimeter typically maybe 50 centimeter or the 1 meter. Then almost an electromagnetic wave is reflected on the ground surface. So we have no chance to see the subsurface. So if the UAV-borne radar is achieved, maybe we can see the ground surface condition or the object on the ground surface. I expect many of the explosive materials or the landmines in a battlefield is not buried, but it is on the ground surface. So maybe we have a chance to detect these objects, but it is not a ground penetrating radar. It's a more close to the maybe UAV-borne or close to the airborne GPR, airborne radar, not the GPR.
Thank you. So the next question is by Yasmin. It says, what's the biggest limitation in GPR resolution? Is it the antenna frequency, soil type, or data processing?
All of them is the issue. Yeah. So, selection of the frequency is always most important. So, given the soil, and we have a target, we know the target, and we have to know the rough depth of the target. And considering these conditions, at first we have to think which frequency we should use. So that is a design for the GPR system. So everything is related, but that is quite important.
So I think it's Vignesh. So Vignesh says, will the vegetation plays a major role by obstruction? And if it is not touching the ground, won't the beams scatter?
Yeah. For the landmine clearance, most of the field has a vegetation. But the conventional way of the landmine is using the metal detector. The condition for the metal detector is almost the same for the GPR. So the sensor have to be also very close to the ground surface, maybe 5 centimeters above the ground surface. In order to scan the metal detector sensor 5 centimeters from the ground surface, we have to cut the glass. So for the landmine detection, at first we have to cut the glass, and the glass height will be maybe less than 10 centimeters or 5 centimeters. Then even if you use a GPR, the glass will not affect so much. But if it is a 50 centimeter in a natural size, sensor cannot be scanned. So vegetation does not play so much obstruction because we have to cut it before we land it. I cannot hear your voice. You are muted.
Sorry, thank you for notifying it to me. So there is another question. I'm sorry, we have too many questions, but we're almost to the end. So hardly
okay.
5 more minutes.
Yeah.
The question says, during movement, the motion noise will reduce the accuracy, I guess. How to overcome them?
Yeah, that is also important. So the skill of the deminer is required. So that is the training. Normally, deminer have to sit on the one position and may not move. If you step forward, it is very dangerous because he or she can step into the minefield and it can explode. So they have to stop steadily. And then scan the area about 50 centimeter by 50 centimeter just before the deminer. So if you train maybe 1 day or 2 days, the scanning is very, very stable. So it is not so much problem.
Thank you. Another, it's just a comment that says, thank you so much. And then there is another question by Vignesh, but maybe let's take the question by Amir as we have already taken one of his questions. So it says, as GPR is portable and cost-effective for small-scale surveys, and also what are the limitations of GPR to mining detection?
Sorry,
So it just says, I think the question is like, what are the limitations of GPR over mining detection?
Which
Professor
question
Sato, it is a
So
chat
it's in
box.
the chat
It is
box.
written in the chat.
Chat box. At the end of the chat box.
Uh-huh.
Yeah, at the
No,
end.
no.
It is just like the GPR is portable. It's cost effective for small scale surveys. So, but are there any limitations of GPR for mining detection?
I cannot see the question, sorry. The last one?
Yeah, if you go to the chat box, yeah, it should be coming. Yeah.
So sorry, could you repeat the question?
So it says, as GPR is portable and cost effective for small scale surveys, what are the limitations of GPR to mining detection?
Yeah, so still the limitation is not we cannot get the exact shape of the object. If the condition is good, we can see the very good image. But the soil is wet or the very strongly inhomogeneous, we cannot get the very good images. So theoretically or ideally, I said that the GPL can discriminate a metal fragment from the real mines, but in actual cases, in some cases, it does not work so well. Metal detector is a quite reliable sensor and can detect 100% metals perfectly. And there is no way to miss any landmines. So our technology, GPL, is rely on the metal detector. At first, we use a metal detector. Then after, we apply the GPL. So the function of the GPL is increase efficiency, and also it gives information about the buried object before excavation. So that means it will be contribute to the safety of the excavation operations. So a limitation of the GPL is how we can improve the safety and efficiency. In a very difficult condition, it cannot increase the safety or the efficiency. It is almost the same as a metal detector. But it is still worth to use that sensor because we can some additional information. In some cases, if it is very, very wet soil, we cannot see anything. That, to be honest, it can also happen. For example, we are working in Colombia, and in a very wet soil in a jungle, some cases we cannot see anything. So it strongly depends on the condition. Yeah, that's why we have to always think about the kind of the scientific approaches to use this tool.
Thank you so much. I mean, it's already 2, but we still have 2 questions. Do you want to take it, or is it okay if they contact you through different means? What do you suggest?
Professor Sato, which do you like to continue the discussions, or you receive emails by the students?
Yeah, but
there are 2 questions. 2 questions left.
Yeah, if you have more questions, I can continue.
Okay.
That's very kind of you. Thank you so much. Here is a question by an anonymous attendee that says, thank you very much for your presentation on this topic. I have a question. How does SAR-based image reconstruction improve the resolution or reliability of GPR data compared to traditional methods? Is it the recommended method?
Yeah. So as for the GPL, in many applications, quite typical application of the GPL is a pipe detection or the cable detection under the pavement. So in that case, we scan the GPL on one straight line and try to find the hyperbolic curve. It is very in many cases we can see the very clear hyperbolic curve. So it is we do not need the sync aperture radar processing. But for the landmine, it's very different. So it is quite beneficial. We can see the horizontal image of the target, then we can recognize it. So the sync aperture processing really contribute to the discrimination of the landmines. And one more thing that we have found is that soil has a very strong inhomogeneity, but it also contains many small stones or the gravels inside. And they also reflected all the electromagnetic wave. If we see just the B scan without any processing, we see many small deflection from these targets. In the radar terminology, we normally call it the clutter. But if you use sync aperture processing, then these small clutter can be reduced, and then and the landmine image can be more clearly imaged. That is caused by the difference of the size of the object. So landmine is relatively about 10 centimeter in diameter. And if you have this very small gravels, the property of the reflection is very different. So I found that the sync aperture processing has also the function of the reducing the clutter. So that makes the image better. So that is also very important advantage of using sync aperture data processing.
Sorry. Thank you so much. So finally, the last question by Vignesh. So how fast is the post-processing done to view the detection results immediately on mobile phone at site? How it works? And does it need high-end computational power to process?
It is also very interesting questions. I started this kind of work 20 years ago. So 20 years ago, we could use a Windows PC, and we use a laptop window to process this as processing. So data acquisition takes about, say, 30 seconds or something like that. And the sync aperture radar processing on PC 20 years ago took several minutes, and we could see the image. The algorithm is also almost the same. But now we use an Android phone, which is a normal commercial Android phone, and the processing takes maybe less than 1 second. So immediately after data was acquired, we can see the image. That is also surprising to us. But thanks to the development of the PC capability, that this technology is very, very practical now.
Thank you so much. So now I think we've finished asking you all the questions that our attendees asked us. There are just a comment saying, thank you so much, Professor.
Okay.
Thank you, Professor.
Thank you very much.
So thank you.
Thank you very much for very interesting questions. It has stimulated me. Thank you very much. Thank you.
Yeah,
So
Professor
I'd like
Sada,
to
thank you
hand
so much again, for giving insightful answers to a wide variety of questions. So we enjoy your discussions and presentation so much. Thank you again. So dear participants, now it's almost time to finish the fourth webinar of this series. So please join us next time. Next time will be held 11th of June, second Wednesday of every month. Okay. Thank you for joining us today. Okay.
Thank you very
See you
much.
again. Bye-bye.
Bye.
Bye. Thank you, everyone. Bye.
Thank you very much.